It's become increasingly more common for smartphones to be used by intoxicated users, whether that's trying to get home safely, posting on social media, or messaging friends. But alcohol impairs decision making, attention, and memory, and smartphones aren't designed to support users in these moments. In a survey I conducted, over 84% of respondents said that they use their phones regularly whilst intoxicated. They said that they experienced things like sending incorrect messages, posting stuff on social media that they regretted, or struggling with simple tasks like trying to book transport home. The existing digital wellbeing features only tend to focus on stuff like general screen time, and they don't have anything to accommodate the motor and cognitive functions that come alongside alcohol use. This project sets out to address that gap. I wanted to explore how smartphones could be better designed to support these users in their intoxicated states and not be overly restrictive, but instead prevent errors, promote safety, and help people to use their smartphones better in intoxicated states. That led to the creation of the Aware Phone interface. It's a context-aware system feature that is designed to adapt to the phone experience in these vulnerable moments. Essentially, I wanted to look at inclusive design. I wanted to look at the different contexts that users use their smartphones and how design should be better for all of these different contexts. Intoxication is just one of the many that I think needs to be looked at and adapted for design for smartphone and technology to make sure that everything is more inclusive and accessible for the different types of users. The Aware Phone interface adapts the smartphone experience across three key states: setup, drunk mode, and exit. In setup, users define their preferences, like app and contact restrictions, safety settings, and custom alerts. Once drunk mode is active, the system applies these changes in real time, simplifying the UI, enforcing restrictions, and enabling safety features. After the session, users receive an activity summary to help them reflect. I'll now break down how this flow was designed and implemented in technical terms. The system was implemented using the Model View View-Model design pattern, chosen for its clear separation of concerns and compatibility with React Native. The view layer, shown in green, contains the user interface, including the setup screen, drunk mode UI, and session summary. It captures user input and displays the current application state. These inputs are passed to the view model, shown in orange, which manages all the business logic and state transitions. This includes controlling the global drunk mode state, scheduling notifications, calculating blood alcohol content, and managing activity tracking. The view model interacts with the model layer, in blue, which handles data storage and processing. This includes communicating with Supabase for cloud storage, using async storage for fast local access, and performing health-related calculations and tracking logic. Data flows from the user through the view. It's then processed and managed in the view model and saved or retrieved via the model. Updates then flow back through the view model to reflect in the UI for the user. This structure keeps responsibilities clearly separated, supports real-time updates, and makes sure the code is easier to maintain and scale as the project grows. This system architecture shows how different parts of the system work together. When the user sets preferences or activates drunk mode, the information is saved locally so the phone can respond instantly. At the same time, key data, like tracking info and health info, is sent to a server where it's processed and stored securely in the Supabase. This keeps the interface fast and responsive, but also saving useful data for later. The prototype was built using React Native with Expo, which made it easy to develop and test on my device. I used TypeScript for the main logic and JavaScript for the user interface. Then the data was stored using Supabase for syncing across sessions, and async for quick access on the device. I tested everything on a real iPhone using Expo Go to reflect realistic use. Here we have the prototype. The first thing was the drunk mode trigger. Drunk mode can be activated in two ways, manually or through context-aware detection. The manual toggle is shown here, and it allows the user to enable the mode whenever they feel it's needed. This immediately activates restrictions, changes the interface, and locks settings for the duration of the session. The context-aware detection algorithm runs in the background when a user is typing and monitors the user's behavior. It calculates a score based on three factors: typo frequency, how much the phone is shaking, and the time of day. Each of these is given a different weight based on its importance. When the total score crosses a certain threshold, the user is prompted to enable drunk mode. Typos are weighted the highest, since they're the strongest indicator of impaired motor function. Phone shaking and time of day are also factored in, but to a lesser extent. In this example, it shows the user sending a text message and typing something incorrectly. The user was also shaking their phone, and the time of day was late on a Friday night. This all meant that the system responds by gently prompting the user to activate the drunk mode. When drunk mode is activated, the interface simplifies to reduce user error. Only non-restricted apps are shown, and larger icons make tapping easier when coordination is impaired. Users can pre-select which apps and contacts to restrict, and those preferences are saved in the Supabase. During a session, restricted apps disappear and contacts are grayed out. Drunk mode settings are also locked, preventing changes until drunk mode is turned off. All of this is controlled using conditional rendering tied to the drunk mode state, with lock logic handled in the view model. To improve user safety, the safety setup allows users to predefine a designated driver, an emergency contact, and their transport mode. This information is then saved in the Supabase and accessed instantly when drunk mode is active. The large quick access buttons at the bottom of the drunk mode screen use these safe preferences automatically, so calling your designated driver or sharing your safety information just takes one tap. Behind the scenes, this data is stored as a structured object and triggered through handlers in the view model. To increase customization, users can set custom alerts like reminders not to text someone or overspend. The system also includes built-in well-being prompts like drink water. Alerts are saved in the Supabase and scheduled when drunk mode starts. Right now they appear at once due to Expo Go limitations, but in the future users could choose custom timings or even receive personalized alerts based on behavior using AI. For health recommendations, users can enter their height and weight in the health settings screen to receive safe drinking guidance based on their BMI. Later, during a session, the blood alcohol content calculator uses this data and the number of drinks entered to estimate their blood alcohol concentration. The blood alcohol calculator uses a simplified version of the Widmark formula. It takes the number of inputted drinks and the pre-saved body weight and estimates blood alcohol content using a general absorption constant. All health data is saved in Supabase and used by the calculator when needed, helping users understand their limits in real time. The typo detection system helps prevent confusing or embarrassing messages. As the user types, each word is compared to a dictionary using fuzzy matching, which checks how similar the word is to real words.
It uses something called the Levenshtein distance, which measures how many changes it takes to turn one word into another. If a misspelled word is only slightly different from the real word, like defunk instead of drunk, it automatically gets corrected. But if the word is too far off, it gets ignored because the system isn't confident enough to make the match.
During each drunk mode session, the system tracks actions like messages sent, calls made, and alerts triggered. Each event is recorded with a timestamp and stored locally in a session log. After drunk mode ends, a pop-up summary shows the session duration and tracked activity. Users can also view their full history in the activity overview screen, where session data is visualized in a bar chart, and each past session can be explored in detail. Throughout implementation, two key theories guided how I designed the system: distributed cognition and phenomenology. Distributed cognition sees the interface as a thinking process itself. It offloads things like memory, judgment, and safety prompts onto the system itself instead of the user. This is why the interface includes things like confirmation prompts before calling 999 or before turning off drunk mode, why it includes stuff like tracking logs, or why it includes a simplified UI. This helps support the user to not need their full focus when using the system. Phenomenology focuses on how users feel when they're using the system. Since intoxicated users experience the world differently, with reduced attention, shaky motor control, and narrow visual focus, the UI adapts to these different circumstances. This is why it includes large buttons, minimal distractions, and gentle feedback to make the users feel safe and supported in the moment. For testing, I conducted manual feature testing, and for evaluation, I gathered information through informal feedback from 3 participants. The 3 participants came back and said that they found the layout clear, the safety tools helpful, and the system overall supportive, even when they imagined themselves using it when impaired. I also evaluated the design using Nielsen's usability heuristics, where the system came back with high scores for clarity, simplicity, and error prevention. The results from the evaluation showed that the main improvements should include a help guide and possibly making things like blood alcohol content easier to understand. The technical testing was also conducted throughout and at the end of the project to ensure things like restrictions, notifications, and state management worked as expected. Overall, this project was developed to be a proof of concept, to look if a system-level feature could support vulnerable users without being controlling or intrusive. The core features like the simplified interface, the drunk mode detection, and the auto-correction system, and more, was all shaped by research and theory. Overall, this project has been a really interesting process. It's taught me how to turn complex problems into an actual user-focused design. One of the biggest challenges would be turning the theory and research into actual functionalities that would be good for the users to use and really provide the most from the system that they can get. I think overall I achieved everything that I wanted to achieve from this project, but there's definitely a lot more that I could add and expand on in the future.